Welcome back to The Deep Dive. Today, we're getting into one of chemistry's neatest tricks, really, how we separate things at a molecular level. We're talking about extraction, and we'll use a classic example. Caffeine, making its great escape. Yeah, the whole idea is molecular preference, how a molecule, chooses its home, which solvent it likes better. Our mission today is to really break down those invisible forces, solubility and polarity, that chemists use all the time to separate, purify, isolate compounds. And caffeine from tea, that's our perfect case study. It shows everything.
It really is. And fundamentally, extraction is just a separation technique. It's all driven by those solubility differences you mentioned. And to make it work in the lab, you basically need your target compound, obviously, but also two solvents that don't mix. Immiscible, like oil and water. Typically, one is very polar. That's your aqueous or water layer.
Yeah.
And the other, less polar, an organic solvent. Like dichloromethane, DCM is a common one.
Right, DCM. And the numbers really tell the story here, don't they? It's not just a vague preference.
Oh, absolutely not. The data is clear. Take caffeine. In water, sure, it dissolves, about 22 milligrams per milliliter. But then you introduce DCM, dichloromethane. Suddenly, that solubility rockets up to around 140 milligrams per milliliter.
Wow, okay. That's a massive difference.
It's colossal. So when caffeine has the choice between water and DCM, it basically bolts for the DCM layer. It escapes the water. And that specific choice, that quantifiable difference, is what makes the whole extraction process work so well.
Okay, so let's dig into why it makes that choice. It all comes down to that fundamental chemistry rule, doesn't it? Like dissolves, like.
Exactly. That's the core principle. Polar things like polar things, nonpolar things like nonpolar things. So think about the two environments. You've got water, super polar. Its dielectric constant is really high, around 80. This makes water fantastic at dissolving salts, ions, anything with a charge. It uses strong hydrogen bonds, dipole forces. It just holds on to charged stuff tightly.
Okay, the polar world loves charges.
Right. Then you have the organic world. Solvents like DCM. It's, moderately polar, much less so than water. Its dielectric constant is only about 9. So this environment is much better for dissolving neutral molecules, things that are maybe only slightly polar or even nonpolar organic compounds. And crucially, it tends to reject things that are really polar or have strong charges. Ions just don't feel comfortable there.
So where does caffeine fit in? It sounds like it's kind of in the middle.
It is actually. Caffeine isn't an ion, it's neutral overall. But it does have some polar parts like nitrogen and oxygen atoms, and also nonpolar parts, those carbon rings. But on balance, it finds the moderately polar environment of DCM, let's say, much more comfortable, more like itself than the highly structured, highly polar world of water. It feels more at home there.
It's the Goldilocks zone for caffeine.
Pretty much, yeah.
Okay, so this molecular matchmaking, why should someone listening care? I mean, beyond just being cool chemistry. Well, because this principle, extraction, it's chemistry's Swiss Army knife. It's incredibly versatile. Chemists grab it for everything. Pulling compounds out of plants, cleaning up the product of a reaction, getting rid of unwanted starting materials, isolating molecules for medicines, for food flavorings. It's fundamental.
Absolutely fundamental. Many industries rely heavily on getting pure compounds, and extraction is often the first, most powerful step.
So how do we actually do it? You mentioned the two solvents. What are the main techniques?
Right. There are two main types. The first one is something, you probably did it this morning, solid liquid extraction.
Like making coffee or tea.
Exactly. Making coffee or tea is solid liquid extraction. You have solid coffee grounds or tea leaves, and you add hot water. The water acts as the solvent, and the heat provides energy. That energy makes the molecules wiggle around more, helps break those weaker bonds holding caffeine and flavor compounds in the solid, and then they can dissolve into the hot water. Simple as that.
Okay, makes sense. What's the other type?
The second type is liquid-liquid extraction. This is the one we usually think of in the lab, using those two immiscible solvents we talked about. You typically use a piece of glassware called a separatory funnel. It lets you mix the two layers, allow the compound, the solute, to distribute itself or partition between the two layers, and does this based purely on its solubility preference, where it feels more at home.
Right, the separatory funnel. I remember those. Okay, so the molecule chooses, but how much? Can we predict how strongly it prefers one layer? I mean, before we start mixing, can we know if it's going to be an efficient separation or, a bit of a struggle?
Yes, absolutely. That's a critical question. And we can quantify it. We use something called the partition coefficient, often written as K with the superscript D. KD.
KDED.
This number is the quantitative measure of that preference. It's defined pretty simply. It's the concentration of your solute in the organic layer. divided by its concentration in the aqueous layer. So KD is C-Tex organic.
Okay, concentration in organic divided by concentration in aqueous. So a big KD dye means?
A big KD day means the compound strongly prefers the organic layer. It will move over there very effectively.
Which means your extraction will be much more efficient. You'll pull more out with each try.
Precisely. A small KDD means it prefers the water or maybe doesn't have a strong preference, and extraction into the organic layer will be difficult.
That predictability is powerful. You're not just guessing. You can actually calculate how well it should work.
Yeah.
That seems vital, especially for things like designing drugs, right? Making sure they go where they need to.
Oh, absolutely crucial. We'll come back to that.
All right, let's put it all together. Let's follow caffeine on its journey. We've steeped the tea. So step 1, the solid liquid extraction is done. Caffeine is now in the hot water. What's next for liquid extraction?
So caffeine's in the water, but it's not alone. Tea leaves have other stuff in them, notably acidic things like tannins and phenols. They contribute to the color and some of the bitterness. If we just added our DCM now, those acidic compounds might actually dissolve in it too, contaminating our caffeine.
Okay. So we need to deal with those first.
Now, this is where a clever chemical trick comes in. Step 2 is adding a base, usually sodium hydroxide, NaOH.
The base, why NaOH?
Because NaOH is a strong base, and it reacts with those acidic tannins and phenols. It pulls the proton off them, it deprotonates them, and when you deprotonate an acid, it becomes a negatively charged ion, a salt, essentially.
And charged things.
Charged things love water. They become highly water-soluble. So by adding NaOH, we convert those acidic impurities into ions that are now trapped quite happily in the aqueous layer.
But caffeine itself isn't acidic, right? So it stays.
Exactly. Caffeine is neutral or maybe very weakly basic, but it doesn't react significantly with the NaOH under these conditions. It stays neutral.
Okay, that's smart. You're chemically tagging the impurities to keep them stuck in the water while leaving the caffeine free to move later?
Precisely. Selective ionization. It cleans up the playing field before the main event.
So step 3,
Yeah.
the main event, adding the DCM. We pour the tea solution, now with the NaOH and the trapped tannins, into the separatory funnel. And then we add our dichloromethane, the DCM. You get those 2 distinct layers, water on top, DCM usually on the bottom because it's denser.
Right. Then you stopper the funnel, then you start the mixing. You don't want to shake it like crazy. Gentle inversion, swirling. The goal is to increase the surface area between the 2 layers. This gives the neutral caffeine molecules plenty of opportunity to bump into that interface and realize, hey, the DCM side is much nicer, and partition across. Because its solubility is so much higher in DCM, it rapidly moves into that organic layer, leaving the ionized tannins behind in the water.
Okay, gentle mixing. But I remember from labs, there are things that can go wrong here, right?
Oh, definitely. 2 main pitfalls with separatory funnels. First one is pressure buildup. Solvents like DCM are volatile, meaning they evaporate easily. When you mix them, even gently, vapor builds up inside the sealed funnel. If you don't release that pressure,
Pop. The stopper goes flying.
exactly. Maybe worse, so you have to vent it frequently. That means turning the funnel upside down, pointing the stem away from everyone, and carefully opening the stopcock to release the pressure. Safety first.
Always vent. Got it. What's the second mistake?
Shaking too vigorously. If you shake it really hard, you can create an emulsion.
An emulsion? Like
Yeah.
mayonnaise?
Sort of, yeah. It's where tiny droplets of one layer get suspended in the other, and they refuse to separate properly. Instead of 2 clear layers, you get this milky, cloudy mess in the middle. It's very frustrating.
Okay, chemical smoothie. That sounds bad. Can you fix it?
Often, yes. The standard trick is called salting out. You add a concentrated solution of salt, usually sodium chloride basically, saturated brine.
Salt water? How does that help?
Adding lots of salt dramatically increases the polarity of the aqueous layer. Water molecules get busy interacting with all those Na+ and Cl ions. This makes the water environment even less hospitable for those tiny trapped droplets of the less polar organic solvent. It effectively squeezes them out. The salt forces the organic droplets to coalesce and reform their own layer, breaking the emulsion. It usually works like a charm.
Clever. Increasing polarity to force separation. Okay, so let's say we avoided emulsions, vented properly. The caffeine is now mostly in the DCM. What's step 4?
Step 4 is simple separation. You let the funnel sit so the layers settle completely, nice and sharp. Then you carefully open the stopcock at the bottom and drain off the lower layer, the DCM containing your caffeine, into a clean flask or beaker.
Done. But is that DCM layer pure caffeine dissolved in DCM?
Not quite.
Yeah.
There's always a tiny amount of water that gets dissolved in the DCM layer, even though they're immiscible overall. It's usually just trace amounts, but it's enough to be an impurity. So step 5 is drying the organic layer. We need to get rid of that trace water.
How do you dry a liquid?
You add a solid drying agent or dehydrating agent. Common ones are anhydrous magnesium sulfate, MgSO4, or sodium sulfate, Nu2SO4. These are salts that have a very strong affinity for water molecules. They basically act like tiny sponges, grabbing onto any water dissolved in the DCM, often forming solid clumps called hydrates.
So you just swirl it around until the powder stops clumping?
Pretty much. When you add fresh drying agent and it stays free-flowing like fine sand, you know it's absorbed all the water it can find. The DCM is now dry.
Okay, try DCM plus caffeine. Now we just need the caffeine.
Yeah.
Step 6.
Step 6 is evaporation. You carefully separate the liquid DCM from the solid drying agent, usually by just pouring it off, which is called decanting, or sometimes by quick filtration. Then you gently remove the solvent. You can let it evaporate in a fume hood, or use gentle heating, or often in labs, a rotary evaporator, which uses vacuum and rotation to speed it up. What's left behind when the DCM is gone? Your crude caffeine crystals.
Crude caffeine. Okay, now before we talk about making it less crude, let's quickly touch on efficiency again. You mentioned K-ini. Does how you do the extraction matter volume-wise?
Massively. There's a really important principle here. Let's say you have 60 milliliters of DCM to do your extraction.
Okay.
Is it better to use all 60 milliliters in one go, or say use 20 millimil 3 times?
My gut says doing it 3 times might be better, like rinsing something sticky multiple times with less water instead of once with lots of water.
That's a perfect analogy. Rinsing syrup out of a cup. 3 small rinses work way better than 1 big one. It's the same in extraction. Doing multiple extractions with smaller volumes is always more efficient than one extraction with the total volume.
Why is that chemically?
Because each time you add fresh solvent and mix, you allow the system to reach equilibrium, again, based on that halogenicity time. By doing it 3 times, you're establishing that favorable partitioning equilibrium 3 separate times. You pull out a good fraction of the solute the first time, then you add fresh solvent and pull out another good fraction of what's left, and so on. One big extraction only lets that equilibrium happen once. Mathematically, multiple extractions always remove more total solute.
Right, maximize the number of times you let that preference do its work. Okay, smart. So we've done our efficient multiple extractions, dry the DCM, evaporated it. We have crude caffeine, still impure though.
Yes. Crude means it likely still has small amounts of other things that maybe had some solubility in DCM or just got physically carried along. So the final step for really pure stuff is usually recrystallization.
Recrystallization. Sounds fancy.
It's elegant, actually. You take your crude solid, dissolve it in the minimum amount of a suitable hot solvent, just enough to get it all dissolved. Then you let that solution cool down very, very slowly. As it cools, the solubility of the caffeine decreases. Because the cooling is slow, the caffeine molecules have time to find each other and arrange themselves into a highly ordered pure crystal lattice. Impurities tend to be excluded from this ordered structure. They don't fit properly, so they stay behind in the cold solvent. You then filter off the pure crystals.
Like building with perfect Lego bricks, the odd-shaped ones get left out.
Exactly like that. And how do you know if you succeeded? If you really have pure caffeine.
Taste it. No, probably not in the lab.
Definitely not. You measure its melting point.
That's right.
A pure crystalline compound has a very sharp, specific melting point range. Impurities disrupt the crystal lattice and typically cause the melting point to be lower and occur over a broader temperature range. So a sharp melting point right at the known value for caffeine tells you, yep, this is pure.
Okay, melting point is the purity check. So from tea leaves to pure white crystals, that whole journey relies on understanding solubility, polarity, and that Katie line. It